Uh, Thanks for coming, everyone. Really happy to be here at OpenSearch I'm JR, and I'm joined with Karan. And today we're going to be talking about how we used OpenSearch to enable a scalable and machine learning-driven search experience at Coursera. So yeah, let's get started. So Coursera's mission is to transform lives through learning, and our job on the search platform team is very simply to help learners find what they want to learn. And this can be tricky sometimes. We have thousands of courses, specializations, degrees, guided projects. So our question is, how do we surface the most relevant content on top so that our learners can find what they're looking for? So that's the underlying question. How do we deliver more relevant search results? Maybe a very classical question for those of you that are acquainted with search. But I can give a personal example of the limitations of our previous search implementation. So I learned how to play guitar on Coursera 10 years ago now, I think. I think I was back in high school or middle school, can't remember. I won't date myself here. But I decided to continue with that learning journey and search up how to play jazz guitar. So naturally, I went to Coursera. I was like, okay, there has to be content on playing jazz guitar. And it couldn't, like our previous search implementation wouldn't return results back. And this is just one example of the limitations of our previous search implementation, which is entirely keyword-based. So there were no lexical matches in our course content catalog that contained the keywords jazz and guitar. This is one benefit of using OpenSearch. We're using the neural query to do semantic search as well. But before we dive into our OpenSearch implementation, Karen's going to talk a little bit more about our previous search architecture.
Hi guys, my name is Karan. Thank you, JR. So I'm going to talk about the limitations of the platform we used previously before OpenSearch. So this vendor that we used only had like keyword matching previously. So there was no, as JR mentioned with the example as well, there was no semantic matching. There was no meaning matching from the documents to the query. And then there was only keyword matching. So the keywords from search query were being matched up to the fields, description fields or title or whatnot from the documents, and the documents were fetched based on that. There was no real ML capability to rank documents. So most ranking that we did with this platform was rule-based. So we could define rules that maybe promote some documents over others. But it was harder to aim for maximizing a metric, for example, like revenue or enrollments. And the next point I think are true for most third-party vendors we use. It's difficult or kind of scary to send IP data to this platform, so personalization could not be possible because we could not really share the user behavior data with this platform. And again, since it's third-party vendor, if we base all of our pipelines based on this vendor, if this vendor ceases to exist eventually, sometime in the future, transitioning the pipelines to a new platform would not be trivial. Could result in sort of vendor lock for us. Next, JR is going to talk about the details of how OpenSearch solves for these problems for us. JR? Sure.
So let's dive into the fun part. I'm going to give like a high-level overview of how our new search architecture works to address these limitations, and then I'm going to dive into like the component level of what services we use and how they interact with each other to power our new search platform. So you might be familiar with this kind of ranking-based search architecture, ranking-heavy search architecture. So our query comes into our backend search service, which then routes requests to OpenSearch. Again, now we have the power of semantic matching with the neural query type. And we do this by generating embedding fields for certain course metadata that we want to capture the semantic meaning behind, like name and description. But we also decided to keep that lexical matching part of our search, just because the search, the types of searches that people on Coursera are doing are still very, very keyword based. So we still want to support that with our lexical matching. So we combine those results together with hybrid search. I'm going to talk a little bit more about how we're doing hybrid search later, but the next part is that we go into aggregations and filtering. This is really essential to power faceted navigation on our site. And then this is the fun part. This is the re-ranking part. So we follow a technique called cascade ranking, where we take some top K of all the matches that come back from OpenSearch and then rank them with a more expensive model. You can see how it's not really feasible to rank all the documents that come back from OpenSearch with that heavy model. We're still constrained with latency. We target for less than 200 milliseconds of P99 application latency. So we follow this cascaded ranking. We can have multiple stages of this. So we can take some top K, so top 100 results, rank that with maybe a tree-based model. Then next take top 50 for a deep learning model, et cetera, to really surface the most relevant content on top. And you can see that with these machine learning ranking models, we're taking things from a feature store. We have a query feature store, content feature store, and now we can enable personalization through the user feature store. So the last step on top of this is our business rules engine. There's some queries where we still need that level of granular control, where we want to boost and pin products to a certain position. So that's the final override here that we make. And then the results get back to our learners. So let's dive into the online flow of how a search query comes into our backend and is returned back to our learner. So we start with our query, comes into our backend. Again, we resolve the filters, aggregations, pagination, all very important for faceted navigation. And next, we generate the final query DSL. So we utilize the search template feature on OpenSearch to do this. And essentially what we do is store that base query DSL containing all the fun stuff, the nitty-gritty of our keyword query, our null query, and as well as the weights. So we have field boosts. We also have individual weights for each subquery. And one thing that we do is we leverage the learn to boost technique to find the optimal weights for each of these values, which Karan will talk about a little bit later. So once we resolve that final query DSL, now we can actually retrieve the documents. So again, we're doing hybrid retrieval here. You can see that in our keyword queries, we have like a name, a classical name metadata field. So we match on like name, description, course instructors, the skills that are course teachers, and so on. And then we take the most important fields, so name, description, for example, and compute the embeddings for this. And again, it helps us capture the semantic meaning behind these fields. Next, we actually combine this step with our light ranker. So we decided to rank at this stage using script score to inject to these content popularity features. We found that the number of enrollments, the rating of a course is still super relevant to provide relevant results. So we do this at this stage. This is a simple linear scoring function. Again, at this stage, we want something fast and low latency for our retrieval and ranking. So that's our first pass ranker in a nutshell. And then comes the fun part. We have the heavy ranker, which contains all the ML goodness that maybe you're more interested in. So here we re-rank the top K with a more complex model and features. And what's notable about this part is that we do this at the application level. So we select that top K, and we get those top K results and then send it to Coursera's in-house recommender / re-ranking system called Rexis. So Rexis at Coursera is like an in-house platform that ML scientists and engineers are super familiar with, super comfortable with, very configurable. And we use that platform to power this heavy ranking. The fun part is that it takes care of all the feature enrichment for us, and it sends it to the appropriate re-ranker. Now, under the hood, Rexis is just a wrapper on top of SageMaker. So all of these features that are coming in, they're coming from a SageMaker feature store. And all of these endpoints are just deployed as a SageMaker endpoint. All these rankers are submitted as SageMaker endpoints. In fact, our text embedding model, remember, if you're using the neural query, you need to embed that text before actually performing the search. We host it externally as a endpoint in SageMaker as well. So with this architecture, we have the ability to add even more re-rankers on top. For example, a deep learning model, maybe even as an extra cascade ranking step, maybe a third pass ranker on top of our heavy ranker. So today, our heavy ranker is a tree-based model trained with learning to rank, which Karan will also talk about a little later. Heavy ranking is expensive. We're not using the search engine query cache here, so we need to cache it ourselves. Here we use Redis. This really helps us speed up performance for our most popular queries. And then we apply our business rules on top. So this is just how a query comes into our backend and how it's returned back to the learner in the online flow. Another really important part of our architecture is the offline flow, where we heavily leverage Databricks. So we use Databricks for our search indexing pipeline. So whenever a new course is published or launched, we send it over to get indexed by our search index and compute the embeddings for all the course metadata we want to perform neural searches on. And then the output of our light ranker is going to be that search template with the learned boost weights. And the output of our heavy ranker is going to be that SageMaker learning to rank endpoint. So you can see that all the training and deployment happens within our Databricks environment. So that's our search architecture in a nutshell with OpenSearch. Karen's going to delve into a little bit more about how we're doing learn to boost and learn to rank, as well as the business rules engine.
Yep. So I'm going to talk about how our Coursera search at Coursera uses templates, for example. We heavily leverage search templates for us, which means that we have a base template that we deal with. And one second, yeah. Base template, which is trained, and it's a combination of different queries. Here's an example of the base template we use. As you can see, it has a neural query, a multi-match query, which is more of a lexical match, and other stuff around it. It's like a hybrid query DSL that we can plug in parameter values to eventually create a query which we can fire to OpenSearch to get the relevant results. There's an important factor here is called learning to boost. So how do we identify? So as you can see in the multi-match thing, there are boosting values defined for different fields of the documents, which means that which field will be checked more or less for a search query for matches. And these boosting values are actually decided by our ML model during a process called light ranking. And light ranking is a process where we fire multiple queries, compare the results of those queries with a judgment list that we have, and then decide that, hey, for this field, this value would result in the best or most relevant documents. So yeah, we create this DSL every day, and then we use this. We have a pipeline we have where we upload it to OpenSearch, and then we use it for our queries. The next part of this process is also query segmentation. So given we have this DSL, it's possible that this DSL works better or worse for different types of queries. So it's possible that we might want to have different DSLs for different types of queries. That's something we call query segmentation. And then we can choose, so on the fly, we can use an ML model to choose which DSL to use for what type of query, and resulting in more relevant results for the learners. Next up is the business rule engine. So business rule engine for us is hosted inside our search application, which is a layer beyond OpenSearch. So there are different types of rules we're trying to handle, and at different layers. The two layers are called pre-processing and post-processing. So again, these are different use cases, and they're being handled at different layers, pre and post. For pre, there are mainly three types of rules that we're trying to handle. First one is query rewriting. So it basically means that when a user types in a query, we try to understand what they could mean based on some stored rules and modify the query term before hitting OpenSearch. So, for example, if somebody searches for like UCB, and which could not really result in most relevant documents, but we understand that the user might be searching for University of Berkeley, for example, or something. So we transition or rewrite the query before firing it to OpenSearch. And the other type of pre-processing business rule is called flexible filtering, where we can apply filters while going into OpenSearch. For example, if somebody searches for marketing degrees, so while this will fetch marketing content, but on the way in, we'll apply, hey, only fetch degrees. Apply filter, degrees equal to true. So the result set will only have degrees that are marketing related. The third type is called preferential boosting, which is a more lenient version of the flexible filtering, where we don't filter out the less relevant or not relevant results. We just downrank them. So we uprank the relevant results, and we downrank the not relevant results. So for marketing degrees, the degrees will come on top, and other courses will come after that. There's also a post-processing part of the business rule engine, which is mainly to serve business needs. So if some university wants their results to show up at position 5, for example, for a query term, so business rule is capable of pinning results in the result set. So on the way out of OpenSearch in the result set, via this application, we can plug in a certain course that we intend to promote at that position. So this is more about the business rule engine, how it's impacting our business rules and enrollments and more metrics. Next, I'm going to talk about why we chose Rexis over the default LTR plugin that OpenSearch already provides. So Rexis, as JR mentioned, is Coursera-hosted, SageMaker-based recommendation engine. And we chose this over the LTR plugin, which is hosted inside OpenSearch due to a few reasons. We also had to go through some trade-offs that I'm going to talk about here. So first of all, the models, right? Our recommendation engine has a lot more modal flexibility. We are able to use more complex models, while OpenSearch only supports linear and tree-based models. And again, so because this is in-house project or engine, we already have a paved path for using SageMaker from Amazon, and LTR plugin would have been something new that we had to experiment with and to understand its performance or the way it works. And again, feature store. So features are super important when you're dealing with machine learning models to deal with. So having a defined feature store, which we already had in Coursera, would have helped us maintain or use the features in our ML model and training. While with OpenSearch, it would have been more complex and mostly queries. And it's also difficult with categorical data, for example, like topics, which has predefined values. It's usually difficult to work with in OpenSearch queries for features. And the other 2 points that I'm going to talk about are more of like trade-offs we made. So we chose, even though LTR probably is a better choice in performance because it's inside OpenSearch, and SageMaker-based Rexis is outside, so there was a network latency we could have added, but we were aware about that, and we thought about it, and we chose to still go with Rexis because of the benefits that we talked about. Next up is pagination. Now, because LTR plugin is inside OpenSearch, so after getting the results from OpenSearch, we don't have to do anything on top of it because OpenSearch can already paginate it. While if we use Rexis, we'll have to repaginate the content or the documents we fetched before serving it to the front end or our clients. Next, I think JR is going to talk about some stories that we found on the way while we're integrating with OpenSearch.
So I'm going to leave off with this last story. As we get closer to actually productionizing OpenSearch here, load testing, very, very important. You want to see how much load your application can take. And the way we decided to do this was through request mirroring. So at Coursera, we use Envoy as our proxy, which has this really neat feature of mirroring traffic that's going to a production service. You can send a copy of that request to a shadow search service. And what we did was that we provisioned a shadow search service containing our OpenSearch integration And we just configured the percentage of traffic that we would mirror from production to the shadow service. And we could monitor the effects on our application latency, our OpenSearch cluster metrics, et cetera. And we're lucky because search is essentially a read-only API for us, so it's super safe to just discard any responses that come back. So the searches that learners do on our platform aren't actually affected by this load testing. They would still get the response from our production application on the way back. So we did come across this mysterious performance issue where we saw, when we were rolling out to 100% traffic, we were seeing that our OpenSearch calls from our application to the cluster was getting highly latent on the order of seconds, which is not ideal for a search application. But the cluster metrics looked totally healthy. Like you can see, our search latency graph is completely flat. CPU and memory utilization was totally fine. Even the thread pool search queue, we thought that was the culprit, but that was healthy as well. And I just wanted to bring up this story as a benefit of using not only OpenSearch, but open source in general, and that's the community. So we eventually narrowed it down to our remote inference thread pool on our cluster. So if you recall, we do an external request whenever we're computing the embedding for a query. So from the OpenSearch cluster, it will call the SageMaker text embedding endpoint that we have. And it turns out that the thread pool that the cluster uses for that request is tuned for local inference and not for external remote requests. And we only found that out through a forum post. I didn't even know forums were still being used that talked about this very exact issue and spelled out the solution for us, which was to scale the cluster up to handle the throughput for this thread pool, but also it linked to an eventual patch in, I think, 2.15 or 2.16, where they changed the HTTP client from async synchronous to asynchronous. So we wouldn't have figured this out without the OpenSearch community. So going back to our original use case, if you want to learn how to play jazz guitar, it turns out with our new search platform, this is what it looks like. You have guitar for beginners, you have jazz improvisation, which is key to learning how to play jazz guitar. Fundamentals of music theory, you do need good music theory fundamentals, how to read sheet music, etc. I'm bringing up this example because it's an example of a semantic match. So within that course, there's no mention of jazz nor guitar as a keyword. And thanks to hybrid retrieval and the neural query, this comes back as a relevant result. So yeah, that's our search architecture in a nutshell. Please feel free to check out Coursera's engineering blog. And if you have any questions, feel free to email us or ask now, whichever you prefer. But thank you.